Hello, people, and welcome back to our second session. So today we're gonna talk about the auxiliary pump functions as of the Schneider ATV310. So actually, I didn't really look at the chat during our last webinar. So for this session, if you have any questions or any things you want to know more about, feel free to put it in the chat. I'll be looking at it this session. Okay, so let's start. Why the auxiliary pump functions are needed? So basically, in a lot of systems, we have running and standby pump sets, which are very, very common in Malaysia, I believe everywhere else. So it provides redundancy where the backup pump can automatically take over when the primary pump fails, because no one likes to be in the situation where the taps run dry. So the auxiliary pumps, they provide increased capacity also, when the demand is a bit too high for one single pump, the auxiliary pump can kick in and provide the additional flow required. So, and there are many, many different styles and functions depending on each and every manufacturers and also panel designers. Some people they design it during using a timer, some prefer a lead lag, some prefer a latching relay, and things like that. So today the main point we'll be talking about is the auxiliary pump, especially with regards to the ATV 310, and to some extent this is actually quite similar to ATV 610 as well. Right. So not all drives are created equal. So many VSD manufacturers they claim to control multiple pumps using one inverter. Like some people, they even claim that one inverter they can control up to six pumps. Okay, I'm not saying that any one of the manufacturers they're bad or something. In fact, the example at the right hand side is lifted straight from the ATV12 catalog. It says they can control one variable pump and one fixed speed auxiliary pump. Okay, it makes a very cost-effective proposal because now instead of one inverter per pump, now you only need one inverter to control all your pumps. Okay, so what is going to happen if this is implemented? Well, the system is good enough for most cases, but has a chance to fail. What I mean by fail and how they fail. So this is one of the key things we are going to talk about today. So consider a variable pump. Okay, now we have pump A and pump B. They are housed in for example, in this example, I have a booster pump set where two pumps they are getting paralleled, goes to a check valve, and then finally there is a pressure transmitter at the manifold. So consider the case where pump A is variable, which means that the VSD drive is connected directly to pump A, and then the auxiliary pump is connected at pump B. So the auxiliary pump B is not variable speed, so it's either it doesn't run or it just run at 100%, which is basically a DOL starter. Okay, so for simplicity's sake, let's say that each pump can supply up to 100% demand, and they are expected to supply up to approximately 200% when both are running. I say unexpected because we all know that pumps running in parallel, you will never get 1 plus 1 equals to 2, this type of situation. You're never going to get it, okay? So this is the case that we're going to use for today's topic. Next, let's say for case number 1. So it's between 0 and 100% demand. So everything is fine. Sky's calm, sky's blue, sea's calm. So pump A modulates from rest to 50 Hertz depending on the demand. So the demand is measured by the pressure transmitter. When there is a demand, pressure drops, pump A ramps up. So since the demand is never exceeding 100%, pump A is fully capable of catering the system all by itself. Pump B is not staged since demand never exceeds 100%. So there is always water flowing through pump A. So we are very concerned about water flow through pumps because when there's no water in the pump and the pump starts, operating without water in it, bad things gonna happen. Okay. Next, we go to case two, which is close to 200% demand. So pump A modulates close to 50 Hertz depending on demand. Okay. Pump B is always running at 100%. So we can safely assume that there is always water flowing through pump A and B. Okay, this makes sense, right? Okay, so pump B you can't control it because it's always 100%, and pump A will always modulate close to 50 Hertz, which is the maximum speed because, as I said, it's close to 200% demand. Okay, so in the first two cases, the system works fine. So what happens when we have a little bit of a unique situation where your demand is between probably slightly above 100%, probably between 101 to 110%. Okay, so in this case, since it is above 100%, pump B will be staged. So pump B will, regardless of the demand, it will always run 100%. So it will cater for the majority of the demand. So which leaves us to the leftover demand, I would say. So what about the extra like 1% or 2% or 10%? So pump A will try to modulate to provide for this 10% or 1% with small percent. So this makes it spins very, very slowly, but it has a problem where pump B is now operating at maximum capacity, whereas pump A is spinning at a very, very low percent. So it might not generate enough pressure to overcome the pressure generated by pump B in the manifold. Simply said, the check valve might not even open. So that brings us to the point where there is a chance for no water flowing through pump A. When you have a zero flow for extended period of time, you can cause severe pump damage. The water starts to boil, the impeller starts to crack, things like that. And furthermore, if you have a frequent start-stop of the auxiliary pump, you might induce an inrush current or a spike. Let's say it fluctuates between 90% and 110%, you're gonna have a very bad, system where things are kicking in and then there's no water flowing through, something like that. Right. So this is a typical situation. It might happen. So what do we do to, uh, take care of this problem? So the solution, make all the pumps operate at the same speed. So if you have all the pumps at the same speed, as you can see from the diagram over there, every point in the manifold, in the exhaust, in the output valve, at before and after the check valve, they are operating at the same pressure. This means that no matter at what speed, of course, we are not talking about extremely low speed over here. We're talking about like the nominal speed of the pump. No matter at what speed, A and B will always be running at the same speed. Same speed, same pressure means that water is free to flow. Okay? So for demand between 0 and 100% is similar. Pump A is modulating freely, governed by the PID settings. Pump B is not staged, so pump B is not moving. So for demand beyond 100%, I don't care whether it's 100 101% all the way to 200%, A and B modulates together at the same speed. So if example for a 110% demand, instead of one pump running at 100%, one pump at 10%, we make the pumps share the load. So each of them will be like 55% or 60%, something like that. Okay, so this guarantees flow across all the pumps, but it calls for a VSD for each of the pump. Okay, so it's not the end of the world because if you have a VSD for each pump, they can add on additional benefits, such as when you have a start-stop situation occurring, your starting current is greatly reduced. Secondly, it can act as a fault and status monitoring. You can like monitor for your load, your RPM, your line fault, ground fault, or something like that. In ATV310 alone, they are, I think, around 35 different fault codes where you can use to monitor your pumps. Okay, and then using a VSD, we can provide you with a soft start and soft stop. The mechanical bearings and the motor lifespan will be greatly increased as well. Okay, so here's the theory behind the ideal booster pumps, which we believe it has to be so. But how does it tie back with a TV310? How do we do it? Of course, I have a demo right over here. I'll get over to it in a moment. Speak louder. Is it soft? I don't know. I have a comment that asked me to speak louder. Uh, okay, I'll try to speak louder. Next, how about your master-slave rotate and trip management? So for example, I have one inverter as a master, one inverter as a slave. So I need to rotate them so that they have even wear and tear. If not, there's always this master is gonna try to run it first, and we have a situation where the master pump needs so much service, and whereas the slave is just sitting there doing minimum work, which is not ideal in terms of maintenance. So in ATV310, we have a local mode, which we can use to interlock with your partner pump trip signal and or timer latching relay. So it means that if let's say pump A is master and pump B is a slave, so pump B actually needs to interlock with pump A in terms of his trip signal, as well as an external timer or a latching relay. So if anything happens to pump A, pump B must immediately take over the master duty. In the example just now, the PID is only active in master, and the slave is just like following whatever the RPM the master is running at. So in this case, you need the function where you can switch between PID mode and local mode. It's a bit tricky, but it's doable. Partly because we only have one analog input where you will have to share between your sensor input and your speed command if it is functioning as a slave. If it is functioning as a master, we expect the sensor to be connected to the AI, whereas if it is functioning as a slave, we expect the AI will be the analog output of the master VSD. Okay? You have anything you want to ask, feel free to just put it in the chat, all right? So pressure transmitter, I have a comment where the volume is still low. Is that a problem? I don't know. Well, I will try to speak louder, but this is, I think, as loud as I can. Um, okay, never mind. Right. So the pressure transmitter must be interlocked to master. Okay. So if you are using a 4 to 20 milliamp type of this pressure transmitter, you will you can't really just loop it around master and slave. It doesn't work like that. And there are so many failsafes that you need to consider so that the control voltage of the each VSD remain separated. So in my example just now, if your sensor requires a 24 volt loop power, don't mix them together because we don't know what happens when one of the VSD, probably the control voltage 24 volt short to earth, something like that. What will happen to the next one? So there's some stuff that you guys as a panel designer or as an engineer you have to design to cater for this. Okay, and then everything that I have spoken about so far, it is implemented. It can be implemented without occupying the high level port, our Modbus RS485, which means that in future you want to like hook up the drive into a BMS or IoT or something like that, the port is still free. You can still use the port. But this comes at a cost of like basically having a lot of relays. A basic system where just one master and one slave. That if you're not talking about like switchovers and things like that, you can actually do it without a relay, which is I have over here. I'm going to show you in a minute. But once we're talking about like switching over master and slave, rotate and things like that, suddenly, bam, you have like 15, 20 relays coming in. Because the more relays you have, the more robust your system is, the more isolated each inverter is, makes that one inverter doesn't affect the next one, at least not too much. If it catches fire or something, I don't think anything can save you. So yeah, so up to now, I believe this is about the rotation. Right. So let's talk about the stage sequence of the auxiliary pump. So when I say stage sequence, it means that our demand is exceeding what the primary or the master pump can provide. So it has to call for a backup. Okay. So at during normal, the pump is always at rest below a minimum frequency. So this minimum frequency is set to prevent the pump from running at a very low speed, which doesn't contribute much and is not efficient and is bad for the motor. Okay, so it's either zero or minimum frequency. It limits how low the pump can go. Once the PID algorithm they command the pump to run more than the LSP, the pump starts modulating between LSP and maximum frequency HSP, which is most of the case 50 Hertz in Malaysia. Okay, so once we exceed the aux pump stage frequency, which basically indicates that our supply is very close to capacity, auxiliary stage delay timer activates. It has a function where you can delay staging the pump. But usually, in my experience, we don't delay staging. We will delay the destaging part because when you're having a shower, your neighbor flushes the toilet, the upstairs neighbor starts washing his dishes. So we don't want to wait for the, the auxiliary pump to come in. We want them to come in immediately. All right. If not, you're gonna have a not so pleasant shower session. Okay, so the aux stage frequency, usually we will set it close to the capacity in the range of 48 or 49 Hertz, which means that if the main drive runs exceeds 48 or 49 Hertz, the auxiliary pump will come in. Okay, so once the delay timer matures, aux pump is staged. By default, this timer is at 2 seconds. I believe it's quite a good value. 2 seconds is okay in most cases. And master pumps drops to LSP, which is the minimum frequency, in anticipation of the auxiliary pump providing additional capacity. So this is a very smart drive. So when it calls in the aux pump, it knows that the auxiliary pump will start to contribute to the supply. It will drop the speed to anticipate for it. Okay, and then after that, further modulations by PID takes over. So you'll see it in just a moment. The sequence is quite pretty, and I think it makes a lot of sense. Okay, so what are the steps of a destaging? Okay, destaging is basically opposite of a staging. So instead of you bring in the pump, now you want to get rid of it because now everyone stops showering or stops using the water. Okay, so once both pumps drops below the auxiliary D stage frequency, which basically indicates that the supply now exceeds the demand. Oh, the aux D stage delay timer is activated. Okay, so typically the D stage frequency will be somewhere slightly above your LSP, your low speed. If your low speed is at 30 Hertz, probably your D stage frequency will be at 31, 32 or something like that. So once you go below this speed, the stage timer activates. Okay, so once this timer matures, the aux pump is destaged. Right, this timer, how long do you want the timer to go? This, I believe, very much depends on your application. If you are having a very frequent changes in demand, probably you might need to delay it for longer so that your auxiliary pump doesn't kick in and stage this stage in a very fast manner. Okay, so once the aux pump is destaged, the master pump raises to the maximum frequency. Again, this is in anticipation of the loss from the aux pump. Okay, so the PID, they know that the aux pump is going off. They know that there will be a drop of supply. So in anticipation of this, it just raises the response of the primary motor to the maximum frequency. And then if it is still exceeding what is needed, further modulation will take over and reduce the speed. So this is a very smart sequencing. Okay, so I believe for the slide part, it's about there for the slide part. Before we move on to the demo, if you have any questions, feel free to just hit it up in the chat. Meanwhile, I will move the webcam to show the setup. Okay, very good. Everyone is clear. Okay, so pardon the shaking. I this mount, the camera mount is like it happened very ad hoc. I just grabbed onto a random phone holder, so it's not very stable. So right now I have two drives. This is a master and this is a slave. So they are connected to a transformer. Because I don't have 415 here, I will just use a very simple transformer over here. So just a quick note, if you do any settings or you want to try out the inverter in places without 415, you can put in 220 at L1 UVW, RST UVW, oh yeah, sorry, at the input. You just put in your line and neutral, but keep in mind that it can power up, but the IGBT will not turn on, which means that if you give it a run command, the drive will not run. Okay, so in my case, I'm gonna show you guys how it runs. So I have a transformer which transform 220 to 415. So just a bit of an interesting story, because I tried to purchase a step up transformer 220 to 415. The guy who sold the transformer say, hey, you guys, you know that you can't do this, right? Because like, he's so worried that I didn't do any calculations in terms of current consumption and things like that. But in the end, you know what I did? I just told him, oh, forget about it. Just sell me a step down transformer instead. 415, step down to 220. Then he happily just sold me the transformer. So basically, transformer is a transformer, coil is a coil. So if you put in 220 as a supply and you put in 415 as your load, as long as your load is within the kVA rating of the transformer, it is fine. So in our case, the drive itself, it is not connected to any motor. I also disabled the output phase loss. Otherwise, it will feel that the drive will trip because there's no load connected to it. It will pretend, it will behave as if the motor lines are disconnected. Okay, so I hope you guys can see the display over here is a bit flickering because of electricity, 50 hertz and things like that. So yeah, it looks fine from my screen. Okay, on top of it, there is a weird number 43203 Right, because I don't have a pressure sensor over here, so this will be an approximation of my sensor values. Okay, so if I'm gonna look at, hang on one second. Okay, so let me try to bring it up again. I don't have a pressure sensor, so I just use mod scan, a popular program to simulate. Hang on, let me just do a little bit of a setup over here. Right. Okay. So what it does, I'm using the output of another inverter to act as a sensor. So if I run the inverter at 100%, I'm getting a value of 1000 going into the analog input of the master inverter. Okay, so if it is a 10 bar sensor, 100% means that my sensor is running at 10 bar. If I'm running at 50, if I'm getting 50% from here, it means that 5 bar. Okay, so the value is a bit wonky because it is expected to have a decimal in between. For example, now I'm running at 45%. So assuming a 10 bar sensor, now my reading is at 4.5 bar. So this is a 0.01 bar resolution. Okay, so look over here. Now I am going to press reference. Okay, So if you can see the flickering, they shows 50.0. It means that my PID set point is at half of my AI value, okay, at 5 bar. So now I am going to pretend that I have something in the manifold. Now is 6.29 bar, which is above 5 bar. So once I press run, the inverter will go up to 30. This is my low speed. Remember, I set it such that the speed of pump cannot go below the low speed. Now, the low speed has a delay timer as well, where I set it at 10 seconds for the purpose of the demo. So now you can see the main inverter 0.0, whereas the auxiliary pump is at dash dash 0. So the meaning is this drive is running, but it is running at 0 Hertz, whereas this drive is not even running. The run command is not even there. So that's why you have a dash dash over here. Okay, so you observe that now I'm going to try to reduce my sensor value. So if I reduce it to below 50, I expect the drive will pick up. So now we pretend that everyone is like turning on their taps and the pressure in the manifold drops. Okay, so I'm gonna turn it like to about, you can see that immediately at 0.01 bar, the drive starts to run. Now it's going to climb up very, very slowly because it's like 0.02 bar different from our set point, which is very, very low. So if I want to speed up the process, I simply drop it further. Now you can see that it starts to pick up very, very fast. And one is at 50, park. The aux come in, and you can see that it drops to 30 and before going off. So now is that running at both pumps are running at the same speed. Okay, it's a bit due to the flickering, so it's a bit hard to see. But from my side, I can see that at most they are like 0.1 hertz difference. Okay, 0.1 hertz is quite negligible in terms of the pump. All right. So as you can see, now if I increase to zero point 0.4 difference, they start to affect the PID. The PID is very, very sensitive. My sensor modulation is of course not gonna be as perfect as a real world scenario. In the real world scenario, it is just beautiful. You can't even see the pressure gauge move. This is how accurate it is, right? So I'm gonna show you how it destage. So if you're gonna make the pump destage, now we have to increase it to the set point, which is more than what we set. Right now it's at 0.01 bar more than the set point. So you can see that now both the drives are starting to ramp down. It's at 42, 43 and going down. So I'm gonna speed it up because to put it probably a little bit faster. Yeah. Okay, so now we wait for a while. You can see that the aux pump will turn off and the main pump will shoot to 50. Okay, now you see it's at 50, but my pressure is still not changing. It's still above, so it is running slowly, going to ramp down. Okay, so now the aux pump is at dash dash 00. It is already destaged, and now after the delay, the main pump stops. Okay, so this is what happens in a very, very straightforward configuration. There is no changeover here. There's just a simple one drive bringing another drive along. So it's not ideal, but it serves as a purpose for today's demonstration. Okay, so if you want to try to design it in a panel with like switchovers and things like that, things will get complicated very, very fast. So always think about what happens if the master trips and things like that. Okay, so up to now, our stream is about to end. So I'll leave it to the floor. If you have any questions, feel free to raise up in the chat. hmm Okay, so if there's no question, I believe that's it for today. So thank you guys for joining, and remember to like and subscribe if you like what we're doing. And I see you guys next week. Bye bye.